Hello, I'm Martin. I will be talking about the progress on the Urban Grammar project, which I do together with Danny as well. It's Danny's fellowship project with the Alan Turing Institute we do at the University of Liverpool within the GDSL. And the whole project roughly revolves around the concept of spatial signatures, which is a classification, a characterization of space based on form and function, it's weird, designed to understand urban environments. I'm not going to talk a lot about the classification itself, but just quickly to get a sense, what is it about? It's a classification which combines a lot of primary vector datasets into a single 16 classes classification, which is deployed across the whole Great Britain. Those 16 classes can be roughly split into 3 macro groups. Periphery, which is composed of 3 groups, from wild countryside to something we call an urban buffer, which is the blue one around the cities. Then we have a group of peripheries, which are the areas like urban sprawls and various suburbias. And then we have city centers. And out of those 16 classes, 9 of those are in city centers. So if you compare this classification to traditional land use land cover classes, where you have, let's say, 40 different types, but only 4 or 6 of them are in cities, we kind of try to turn it upside down and we try to focus on urban environments and say countryside is also important, but for this kind of purpose, not that much. However, as this is based on vector data, and based on very large set of data sets we use in it, it has certain limitations. For example, we use population data, which we can get reliably every 10 years from census. So if we want to create this kind of classification for every year and look at the temporal analysis of this, we are unable to do so. So the second part of the project we are currently in the middle of is focusing on satellite imagery. So quite often, if you say satellite imagery, you imagine Google Maps, which is an image like this one, where we can see a lot of detail about an urban environment. However, this is not exactly satellite imagery. This is aerial imagery from plane, and that's much higher resolution than what is openly available, because the best openly available satellite data set is Sentinel-2, which has the resolution of 10 meters per pixel. It looks like this. These are meters of the square you can look at. So you barely understand what is on the picture. And this is the limitation we have to work with, and because we restricted ourselves within the whole project to work only with open data. So our goal in here is to train a neural network which takes Sentinel-2 data and predicts spatial signature classes. But importantly, at this stage, we're trying to understand the role of geography within training of neural network for this kind of purposes. And there are a couple of questions, a couple of aspects we are trying to look at. And probably the most important one, or one of the most important ones, is the chip size effect. Because as soon as you try to turn kind of geographical problem into neural network problem, you have to sample the Sentinel-2. And this is the illustration of sampling the so-called chips, which is the square portion of the Sentinel-2 over a Liverpool area. And if you work with chips which are 8 by 8 pixels or 80 by 80 meters, you can get quite a lot of them. However, the information in 8 by 8 pixels is not very high. So we can try to go larger, but as larger you go, the less pixels, the less chips you can actually select. So we are looking into the relationship between the size, between the accuracy, and between all these issues we are dealing with in here. Within a couple of different neural network architectures, and the most basic one is the image classification. We take the chip and we try to predict which class it is. The second one is trying to somehow include geography into the issue, and it turns the problem into a multi-output regression, where instead of predicting a single class, we are trying to predict the proportion of a class within each chip, which means that we can sample the whole country theoretically. But it also means that the model can learn collocation because it knows that the light blue, the laser doesn't really work, the light blue is very often next to the yellow one. And this can be translated into the final result. And we are also playing with geographical sliding of chips, which means that instead of going like this, where we have relatively rigid grid, we try to slide the window within the signature boundaries to get multiple chips which are partially overlapping, but it's a unique chip which gives us enough data, because even though we have the whole country to sample from, when we try to get 64 by 64 pixels, we don't have enough chips. So we have to do tricks like this. And the one final layer on top we are playing with is probability modeling. So as soon as you get the probabilities coming from the neural network, those are for individual chips. We are playing with an idea of training another layer of machine learning model on top of that. But for each chip, we take not only we look not only at the probabilities of that individual chips, but also its neighboring chips. And then we include that within the spatial act models, random forest, gradient boosted trees, or even just linear logit. And we look into the effect of spatially lagged second layer machine learning model on top of the neural network. And a couple of previews of the results. I think I can quickly skip this. When we look into the image classification problem, this would be a wild countryside around Liverpool, Manchester, Leeds, and here. It's quite noisy. If you look at the multi-output regression problem, it's much less noisy. And the really funny thing about this is that both models have approximately the same accuracy levels. And we can see the same within the urbanity classes within the city centers. Image classification, relatively noisy. Multi-output regression, quite better. But again, accuracy is the same, approximately the same. So that leads us to another rabbit hole, figuring out how to actually assess these models if the accuracy is the same. So we are looking into a couple of spatial modeling, spatial assessment of the final prediction. And this would be the final map as we would like it to have, but hopefully with a bit less noise that you can look at right now. The modeling we do is kind of showing perspective that is positive right now, but we have tested it only on very disbalanced set right now. So on the left-hand side in here, this is the baseline. This is what comes from the neural network. And you have different precision model, precision to the, you have different precision metrics in here. And every time we look into a single model, we have the model which looks only at a single chip and the one which looks at the chip at its neighbors. And you always see that there is a bump when we include the spatial information in it. It depends based on the model how big the bump is, but it makes us very positive about this approach. And within a couple of weeks, we hope to deploy it to the whole country to get a better sense of how this actually works. So a couple of takeaways we are having from this right now. We need better evaluation of model performance, the one which takes into account spatial aspects of the problem. If you in here have any idea about the probability modeling, I was talking about the layer on top of the neural network, I'd be happy to hear if it makes any sense to you, or if you have any other ideas of how to tackle these primarily geographical issues, not as much computer science issues, we'd be happy to hear them. Thank you.